today again we're going to continue our discussion of phonetics. We know that speech is in the form of sound waves, obviously, because speech is sound. So speech is basically spoken, but speech is about sounds, but it's all about linguistic sounds. And we know that sounds, they can be analyzed in a particular way, but speech sounds have certain properties that non-speech sounds or non-linguistic sounds do not. So in a way, speech sounds are a subset of sounds because of their characteristic properties. And in the last couple of videos, we've been examining and trying to learn about these properties of speech sounds. So the concepts that we analyze here are used in the physics of sound because they're used for analyzing sounds in general. But we use those concepts specifically for the analysis of speech sounds. One of those concepts is fundamental frequency, which is obviously a kind of frequency. We have looked at frequency as a property of sound waves, and we showed that speech sounds can be visualized, and once they're visualized, they have complex waveforms. Complex waveforms may look messy, and you might think that there's no pattern to those waves. But once you zoom in on those waves and look at them more closely, you will see that there is actually a pattern. So to analyze those patterns, you will need certain conceptual tools, one of which is fundamental frequency. So fundamental frequency is a term used in acoustic phonetics and also the physics of sound that refers to the lowest frequency component in a complex sound wave. So it is called fundamental, or F with a subscripted 0, which is, you can read as F naught. Fundamental frequency is the first harmonic. It is the first and the loudest. But you need to know at this point that the fundamental frequency is particularly important in the understanding of intonation, where it closely corresponds to pitch. The fundamental frequency is the lowest frequency of a periodic waveform. When we say periodic, it means that the wave repeats itself at regular intervals. Let me actually show you a waveform. So you see here, you see three waveforms from bottom to top. The first one is for the vowel E in words like see. The second one is for the vowel U in words like who. And the third one is for the vowel A in like the words like caught, taught, sought. In a way, you could say that every vowel has a shape. You could draw the shape. You see, these waveforms are actually a drawing which are related to the sound. So they are the visualization of the sound. In the horizontal axis, you have time in seconds. But we know that speech is so fast that it's better to do it in milliseconds. That's why, although it's in seconds, you see that the actual numbers are small. So the first number is 0, the second one is 100th, which is the 100th of a second. So if you look at these waves, you will see that although they are not a simple sine wave that we showed in previous videos, they still have some sort of pattern, right? So the waveforms of the vowels O, U as in who, and E as in see, at a fundamental frequency of approximately 100 Hertz. I'm explaining the sound waves, so in a way we have already started analyzing speech sounds. When we say 100 Hertz, it means that the waveform repeats itself every 100th of a second. Every wave here, it has taken 2/100ths of a second to say each of these vowels. But in each vowel, the wave has repeated itself twice. In the first 100th of a second, you see that although this is a complex pattern, you have this part which is very dense, and then it goes down and then up and then down and a little up, and then it finishes. Then here at 100th of a second, the same pattern is repeated. You will see the same repetition of pattern in the other two waveforms. In 1 second, you will see this first half of the wave repeat itself 100 times. That's what it means to say that the fundamental frequency is 100 Hertz. So you would say, okay, these three sound waves share the same fundamental frequency, but they look different. Obviously they look different because they are three different vowels, and this difference in form is actually an indication of the difference in quality. So these vowels share the same fundamental frequency, but they have different qualities because they're different vowels. The speech sounds would differ with other speech sounds as well as with other non-speech sounds, sounds from piano, tuning fork, etc. in terms of waveforms, because they differ in quality. So not only do these sounds differ with each other, all of which are speech sounds, they would differ from non-speech sounds. In other words, every speech sound has its own characteristic waveform or wave shape. So you could say that, oh, oo looks like this, all looks like this, and that would be a very accurate statement. The above three vowels have the same pitch though. The fact that they repeat themselves every hundredth of a second means that they have the same pitch, because it closely corresponds to the pitch. So if they have the same fundamental frequency, they have the same pitch. In each vowel, you can see one or two more or less regular waves superimposed on the main pattern. So what does that mean? You see, if you look at the first part, if you simplify it as just a curved line, you would see that inside there's smaller patterns within that. So those smaller patterns are also important for the understanding of speech sounds. In awe, the added wave repeats itself for about 5 times or so for every single repetition of the main pattern. You can count 5 peaks. So the whole thing is one big piece, one big pattern, but within that you have 5 smaller peaks. Since the complex wave has a frequency of 100 Hertz, the smaller wave has a frequency of about 500 Hertz. Okay, let me go back and explain this. So in the case of awe, you see every hundredth of a second, this big pattern, main pattern repeats itself once. But these smaller ones repeat themselves 5 times as many, which means they have a frequency of 500. So as the main pattern repeats itself once, the smaller patterns repeat themselves 5. Their frequency would be 500 Hertz. But that's only in the case of the vowel aw, as in caught. Similarly, if you look at the vowel oo, it has one main pattern, but within that main pattern it has 3 small peaks. So the small peaks have a frequency of 300. In this one, it's 2.5 times almost, so it has a frequency of 250. Generally, vowels are complex sounds that need to be described with 2 or 3 frequencies. That's why I looked at the smaller peaks. In this case, I looked at 2 frequencies, the one frequency of the main pattern and one frequency of the smaller peaks. But this was a basic introduction into the understanding of vowels based on frequencies, most importantly, fundamental frequencies. In the following videos, we will look more deeply into the wave structure of vowels.